Hi, this is Shixing from Amazon Prime Video, and I'll present our work of Movies2Scenes. As a high-level overview, we propose a novel contrastive learning approach that uses movie metadata like co-watch, genre, and synopsis to learn a general-purpose scene representation which can be applied to a variety of downstream tasks. Our key intuition is that we can use metadata to define a measure of movie similarity and use it to limit our search for positive scene pairs to only the movies that are considered similar to each other. This allows us to find positive scene pairs that are not only visually similar but also semantically relevant, and can therefore provide us with a much richer set of geometric and semantic data augmentations compared to previously employed augmentation schemes. Our learned scene representation consistently outperforms existing state-of-the-art methods on a diverse set of tasks, evaluated using multiple benchmark datasets. Diving into details. Movie scene understanding is a task to interpret visual concepts, character interactions, artistic styles, and semantic storylines in movies. It is crucial for a variety of applications such as video moderation, search, and recommendation. However, the long-form nature of movies makes labeling of their scenes a laborious process. For example, in benchmark datasets, there are on average merely around 200 labeled scenes for each category in corresponding tasks, which limits the effectiveness of traditional end-to-end supervised learning approaches. Moreover, directly using existing large-scale pre-trained models for movie scene understanding tasks does not prove to be effective given the large domain gap between internet and cinematic content. In this work, we propose a model that is trained on over 5 million movie scenes comprising more than 45 million shots. More importantly, these scenes are automatically identified from 30K movies in our MovieCL 30K dataset. That is, our model does not require any manual annotations and only relies on commonly available movie metadata like genre. Specifically, there are three main stages in our approach. First, we train a shot encoder offline to provide appearance-based representations using unlabeled movie shots. Second, during movie-level similarity learning, given a movie pair M1 and M2, we divide them into their constituent shots X1 and X2 respectively. We extract features of these shots using a fixed shot encoder, followed by a learnable movie encoder, and then take dot product to create shot adjacency matrix. After pooling and flattening operations, we get an output vector V, which is then regressed against defined movie-level similarity between M1 and M2. During inference, similar operations up to flattening will be processed for automatic similar scene pair selection. With the automatically selected similar scene pairs, we further train a scene encoder separately by contrastive learning, and this scene encoder will then be used for all downstream tasks. For experimental results, we first show some qualitative examples of semantically similar scenes found by our approach. Here's another example. This is one with a different theme. These are ones from the same series. This is one more related to plot. We can see that these scene pairs are not only visually similar but also semantically relevant, and this contributes to the effectiveness of our representation on downstream tasks related to semantic scene understanding. For quantitative comparisons with state-of-the-art results on benchmark LVU dataset, there are two main parts of the table where each model is considered as either an end-to-end learning or a representation-based approach. For end-to-end methods, they generally use a smaller scale of pre-training data, followed by end-to-end fine-tuning on downstream tasks in LVU. Thus, they require to train a higher number of parameters during supervised training. A higher number of frames per scene is also used in end-to-end models, which enables them to incorporate more information. For representation-based approaches, we compare with some recent large-scale pre-trained models using various scales and modalities of data. We extract features from their fixed visual encoders and learn a simple MLP for downstream tasks, which significantly reduces the number of parameters needed during supervised training. Overall, our approach offers an average improvement of 7.9% on the 7 classification tasks and 9.7% improvement on the 2 regression tasks, which further validates the effectiveness of our learned scene representations. Going forward, we will further improve the efficiency of our approach to help it scale even more. We will also explore other types of movie metadata to find a representation effective for additional downstream tasks. Furthermore, there are additional long-form content like music, news articles, and books, where acquiring fine-grained labels is costly. We will apply our approach on these long-form content to enable downstream tasks from multiple domains.